semester. So this is awesome. This is great to see everybody here. And we're in for a treat today. Dr. Glazner's talk. But before I introduce him, I want to let you know about a couple upcoming events. Monday is a big day in the GEOS department. We have a master's thesis defense from John Kelly right here that will be in this room on Monday at 3 o'clock?
3 o'clock.
At 3 o'clock. So that is open to the public. You can throw any vegetables or fruits are allowed.
Can we read them first? Orange slices will be provided.
Yeah, oh, there you go. Also, this particular seminar, the GEOS seminar, will be continuing back on its regular day on Monday, which will be Hari Har will talk a little bit about his work with cannabis cultivation and all the regulations that go along with that. So we'll be continuing our GEOS seminar on Monday, 5:30, with that on Monday. And then 2 days after that, we have another speaker at Panagetti's that we'll be co-hosting with GRA, Northern Sac Valley branch of the Groundwater Resource Association. So look online. I usually show it on there, but that's okay. We can do this. Look online. It's a very packed schedule towards the end of the semester. Because the following week, our GEOS seniors, our GEOS students will be talking about their trip to Hawaii. And we all want to know about what they did on their trip to Hawaii. They just got back. So I'm looking forward to that. And then finally, our current graduate students will give a presentation on their proposals. Yep.
Travis is defending on the 18th as well.
Travis Moore defending on April 18th. Okay, good. So look for more events that are occurring in the GEOS department. Well, with that, we are very fortunate to have Dr. Allan Glazner here from University of North Carolina at Chapel Hill. This is a distinguished lecture series sponsored by the Mineralogical Society of America, and Dr. Glazner will talk more about that. But Dr. Glazner is the Keenan Distinguished Professor of Geological Sciences at the University of North Carolina at Chapel Hill. He is now emotionally over the UNC loss in the Sweet 16.
The ACC won the championship.
The ACC's championship, so he's over that, so I think we're good. Wow. So, but for those of you not in the world of sports, he received his BA from Pomona College in Southern California, his PhD just over the hill, just across the basin from UCLA, and then straight out of graduate school, he went to UNC Chapel Hill, and he's been there for 26 years. No?
37.
37 years. Sorry, my bad.
It was 26 when I went.
I got you. Well, as you'll see, his research focuses on magmatism tectonics of Western North America. His name's all over the literature. I was very pleased to talk to him earlier about just other places in California. He's extremely knowledgeable about California geology in general. He has co-authored 3 geology underfoot books of California regions. So we are, again, very fortunate to have him here. He loves trips in California, loves to lead trips, field geologist at heart. And then with that, we're going to learn a lot about plutons. So with that, Dr. Allan Glazner.
It's really great to be here. I love this part of California. I don't get up here often enough, so I was really pleased to get the invitation to come here. So it's great to see it. And I'll do my best to deal with 2 screens. I'm going to try this pointer so that it'll be on both screens. So hopefully that will work. If anybody has trouble seeing anything or hearing anything, let me know. So Todd said my name's all over the literature, sometimes in good ways, sometimes in bad ways. What I find most interesting in science are things that we know that we're all taught that turn out not to be true. I started my career as an undergraduate looking at the relationships between plate tectonics and magmatism in Southern California, which is one of the places where those relationships were first developed, and I slowly realized little bit when I was a student, but much more since then, that a lot of those classic relationships between subduction and volcanism and all that were developed in California were based on really spotty data and turned out not to be true. So that's something I pursue. I worked on volcanic rocks for a long time and have slowly worked my way deeper into the crust. And as Todd and I were talking, I used to work a lot in the Mojave Desert, which is basically a shooting gallery and a place where people go to change their oil without bothering to use a drain can to drain the oil into and so forth. And now I work in Yosemite National Park mostly. It's been quite a nice change. And I went into Yosemite, as I'll show you in a minute, with the same assumptions that everybody else did, and the data convinced me that a lot of those are wrong. So what I want to talk about today is the concept of what plutons are that's come out of my research group, which is me, Drew Coleman, geochronologist at North Carolina, and John Bartley, a structural geologist at Utah, and a whole bunch of our students. And this concept, I deliberately, provocatively say a 21st century view of plutons. To contrast with this view, this is the first of what I would call big-red-blob concepts of plutons. So this is from Charles Lyell's classic textbook, Elements of Geology, 1839. This is a hand-colored photograph of a hand-colored frontispiece of the book. I went to the rare book collection and got it out. Found out those are all hand-colored by people with pencils. And it shows an erupting volcano with a blob of magma feeding it underneath here. So this red blob is intruding a pink blob, which is an older pluton. So the red blobs are plutons intruding metamorphic rocks with sedimentary rocks on top of them and so forth. This is the first place in the literature that I can find a connection between plutons and magma chambers and feeding active magmatic systems at the surface. And this picture is sort of persisted, kind of unchanged. It's a very appealing picture. It makes sense as something like Mount Shasta or Mount Lassen has an active body of magma underneath it like that. And this has been reproduced thousands, tens of thousands of times in books and papers and TV shows and everything ever since. And I think it is fundamentally flawed. So I'm going to spend a lot of the talk talking about that and what that tells us we should be doing when we're in the field looking at plutons, like we're in Yosemite looking at the granite walls. What do they mean? What are we looking at? How was that part of the crust constructed? I'll talk a little bit about MSA. This is an old 1980 cover of Mineralogical or American Mineralogist published by MSA. It's the 100th anniversary of MSA, so they've had a bunch of centennial papers and so forth out. And it's now renamed itself the Journal of Earth and Planetary Materials because it's not just about mineral names and systematic mineralogy and so on. It's actually really quite a vital journal, and if you haven't looked at it in a while, I recommend you take a look and see some of the cool papers. I just recently co-authored a paper on lunar petrology in there. It has a lot of Martian and lunar stuff and so on. But this issue has my second paper. I had a paper based on work I had done as an undergraduate at Pomona. It was my very first publication in AmMin. And this was one stuff I did when I was TAing petrology at UCLA and all. So I have a soft spot for AmMin in my publication career. My next paper is coming out in June in American Mineralogist. So it's a great journal. Take a look at it. So here's Yosemite. I'm standing at Glacier Point. I'm sure many of you have been there. And it's the top of a 1,000-meter cliff. 1,000-meter cliff that has people at the bottom of it, staying in cabins and so forth. So that's kind of a problem. And looking across at Half Dome here, and it's 1,800 meters from Half Dome down to Mirror Lake there. And I went into Yosemite with a few graduate students back in the 90s, carrying the same assumptions that everybody else had, that this rock, and standing at Glacier Point and looking to the east, everything in that picture that's a rock is part of the Half Dome granodiorite named for Half Dome. And it all kind of looks the same. And it's all mapped as one Pluton, I'll put air quotes around that. One map unit, one body that looks like the half-dome granite diorite, and there are contacts like almost right under my feet here with a unit to the west. And way back in the distance, this is Tenaya Peak, that's all half-dome. Sorry, this is Tenaya Peak, that's half-dome. And there's a little bit of non-half-dome over here on Mount Hoffman, but everything else in this picture is that one Pluton. It goes for over 20 kilometers. It's a gigantic body of granite diorite that all looks the same. And those have been interpreted and are still interpreted by most people as the frozen remains of a big blob of magma that came into the crust somehow in a short period of time back in the Cretaceous, maybe 92 million years ago or so. And that is the concept that I want to talk about today. So I went in here with my student Walt Gray, and we thought we've got 1,800 meters of relief from the top of Half Dome to the bottom. So we're going to sample as close to vertically as we can and look at vertical variations, because dense minerals should have sunk to the bottom of this magma body, and light, water-rich granitic liquid should have percolated to the top, and xenoliths from the roof, you know, the rock that it was intruding should have fallen to the bottom. We should see all this vertical variation that the big blob model predicts, and we didn't see any of that. We didn't find anything that was consistent with that, and that was a puzzle. So that's kind of where this started. I work in the park a lot, and one of the people I work with is Greg Stock here, the park geologist. Greg is a geomorphologist, and he was hired to deal with rockfall hazards, and this is a particularly big rock that fell down in 1980 along the river route into the valley there, so that's the Merced River in the background. Nobody was killed in this one, but there have been some deaths from rockfall, as you're probably aware, in past decades. And so Greg has been working really hard to move people away from places. It's really not very hard. You like don't have people sleep at the bottom of Glacier Point Cliff, you know, so they closed a lot of those cabins and so forth and turned some of the housing quarters for employees into storage and all. And they've really reduced the risk of people to rockfall, but it's still always there. And one thing Greg pointed out to me was that you cannot make a rock this big, a boulder this big, in any average rock. This has to be an exceptionally strong, unfractured, unfaulted, unjointed body of rock. And that led to some of the work we're looking at now, which is how is it that the rocks in Yosemite are so strong compared to most places in the world? You can't make 1,000-meter cliffs in just anything. You can't make it in sedimentary rocks, most metamorphic rocks. You can't make it in most granites. There's something special about Yosemite that gives you this unique landscape. And so we've been working on how the bedrock geology that we're working on influences the geomorphology and hydrology and all the different surface aspects of the park. And so Greg and I have worked together on that. We have a project on Half Dome right now that's ongoing. So let's talk about the general concept of what plutons are. So here's a piece of the Chico sheet of the Atlas of California geology, and so we're right about here, I think, more or less. Paradise is on here somewhere. There's Paradise. So these blobs, they're orangey blobs, are various plutons mapped in the mountains east of here. And you can see the scale there. So this one, this is the Granite Basin Pluton. It's several kilometers across. The Merrimack Pluton is maybe 10 average kilometers across. And they intrude the green and blue and green and pink rocks in there, which are the wall rocks into which the plutons came. And looking at a map like this, and this is not at all unusual, it looks like those are blobs. You know, you're looking at an eroded surface through semi-spherical blobs of magma that have been eroded down and produce these kinds of oval outlines like that. And in some places they push the rocks around them aside, and in some places they cut them off, and so forth. And that's kind of very consistent with the idea that plutons are the frozen remains of these big magma chambers. And if you look at the rocks in those, this is a picture of the Half Dome granite diorite. from Yosemite, and it's a beautiful igneous rock. It's got big black crystals of hornblende and biotite, and it's got pink potassium feldspar and white plagioclase and gray quartz and just all the things you would expect. And that's a classic igneous texture. It's by definition an igneous texture, but what I'm going to argue later in the talk is that it's a highly metamorphosed igneous texture. It's just by definition igneous, but it's been through a long metamorphic history, and the crystal boundaries have moved around a lot to give you the texture that we see today. So I've got couple of word slides here. I will have very few word slides, but I've got to emphasize a few things here. And I want to talk about tacit assumptions about Pluton. So tacit is unspoken assumptions. They're things we don't need to say because we all know they're true. We all have the same assumptions. So here are tacit assumptions about plutons. One of them is that plutons are crystallized magma. That's one I'd go with. You know, I mean, it was back in the 1700s that granites were thought to be sedimentary rocks deposited at the bottom of the ocean, and in late 1700s, 1800s, that debate was kind of mostly pushed on the igneous side, and that's a good assumption that I'll go with. I'm not going to question that one. The rest of these, not so much. So another one, they're intruded as large, mobile, meaning the magma can move, molten blobs, and I just showed a map that is consistent with that. Another is that the mapped boundaries of those blobs, like on the map I just showed, are the boundaries of that blob of magma. Another is that magmatic differentiation, so in other words, the processes that convert one composition to another that you learn about in intro geology, you know, crystal settling and those sorts of things, that kind of differentiation happens at the level you're observing. So when you go out and look at the bald rock Pluton or whatever, if you see compositional variations, the assumption is that that stuff came in as magma, and then those processes at that level caused the variations you see. Another is that magma chamber floors are loose piles of crystals. So you've got this room full of magma, crystals start forming, the denser ones settle to the bottom and make a pile of layers on the bottom, okay? That's a very common assumption. Consistent with that is that when you see layers of crystals, when you see bands of crystals in outcrop, which is very common, that those represent these sedimentation processes. They're essentially igneous sedimentation on the bottom of a magma body. Another is that granite textures tell you things about the sequence of crystallization, and a particular example of that is that when you pick up, or when you see a potassium feldspar crystal that has a cross-section as big as this phone, which is not that uncommon, because they're so big and they have nice crystal outlines that they form very early in the crystallization sequence. That's what you're taught in petrology, so it must be true, right? It's not. Another one is that fresh-looking granites, like the half dome that I showed you, are unmetamorphosed. Very common assumption, makes perfect sense. And finally, if you see a granite that looks undeformed, that it is actually undeformed. And I will show you examples where that is very clearly not the case. So these are assumptions that most everyone has. And I want to give you some alternatives, just ways to think about plutons, and just encourage you to have an open mind when you're looking at these fundamental building blocks of the Earth's crust. The first one is that a mapped Pluton is analogous to a sedimentary formation in the sense that it's just a convenient mapping unit that you can draw boundaries around. Sedimentary formation might represent one facies. It might be like a beach sand facies, and it's all representing the same environment and so on. But it also might just be a collection of beds from different sources and all that happen to lie between two other formations, and somebody just said, let's just call that the so-and-so formation. They aren't necessarily genetically related. A typical Pluton is commonly highly composite, meaning it's not made of one big blob of magma, it's made of lots and lots, thousands, tens of thousands, millions of separate little injections. Composite. And those injections might come from different sources. It's really common to find dikes that have a mafic component, say a diorite, an intrusive equivalent of an andesite, with granite at the margins. Two different magmas from different sources that happen to flow in the same conduit. Maybe one of them came up and intersected a body of magma with the other, and then they both took off toward the surface, and then they froze and they ended up dying, freezing in the same conduit. Two different sources, but in the same place. And many plutons are like that as well. They're just magmas that happen to end their life in the same place. The map units that we see in the field when we draw boundaries around are textural units. They're not genetic units. Yeah, not necessarily genetic. So in other words, I'm walking along and I see one granite and then it changes to something else, and I draw a contact on my map. But that's something I can see with my eye. It's a textural unit, not something that's genetic. And those textures are highly modified by late-stage processes. Most granites are igneous and metamorphic. And the layering that we see, they may be deformed but healed. And the layering commonly results from chemical processes, not physical processes like sedimentation. So magma is like the essence of igneous petrology. That's what igneous petrology is all about. And you'd think that we had a good definition of what magma is, right? Everybody has an idea in their head what magma is like. You'd think that that would be well agreed upon by igneous petrologists. Well, it's not. When I'm looking for the definition of something, I often go to the Oxford English Dictionary, which is the world's most authoritative thing, and they have a great definition. Definition number 5, you can look it up, of the Oxford English Dictionary, is magma is a confused or disordered body or mass of something. That's the actual definition, 5, in the OED.
That's great.
It's true. And it's unfortunately really true as far as petrology goes. So, when Mount St. Helens went off, 1980, there isn't a single second of video footage of the eruption of Mount St. Helens. It was right before the giant, shoulder-sized camcorders came out. Nowadays, everybody's got a high-quality video recorder in their pocket all the time. And if you look around, some of the footage you can see of active eruptions is just amazing. I mean, look at this footage. Incredible. Poor guy. I never heard that they made it out.
Did they go to UCLA?
They're too dumb.
There were some birds involved.
There were some birds. Yeah, I cut the clip before the eagles arrived. We'd all agree that if that were real, that would be eruptive magma. And that's kind of what everybody has in their head when they think of magma. But what about this? This is a false color image of an experiment where people were looking at partially melted peridotite, so most of the green is olivine. The red, I've colored it red, is melt. And they were looking at how interconnected the little bodies of melt is. That has a big effect on the physical properties of the rock. There's about 2% red here. Would anybody here call this magma? It's okay if you do.
Certainly not going to flow anywhere.
Yeah, no hands went up. I would not call it magma. Lots of people call it magma, including at least one true igneous petrologist, mostly geophysicists. And I think the reason they call it magma is because they make cartoons like this. This is Yellowstone. This is from oops, sorry, wrong screen. This is from a 2015 paper from the seismic group at University of Utah. And they have a big red blob of basaltic partial melt. This is under Yellowstone. Sitting under an orangey red big blob of rhyolitic partial melt. And they issued a press release. This is a paper in Science. And they issued a press release where they said, and maybe you remember this, there's enough magma under Yellowstone to fill the Grand Canyon 11 times. Now, one Grand Canyon full is kind of a hard concept to wrap your head around, but it's really big, and 11 Grand Canyons full is really, really bigger. And that's really scary because Yellowstone has unleashed 3 super eruptions in the last couple million years, and a lot of prepper lore is that, oh, Yellowstone's going to go any day, and you got to go buy a lot of freeze-dried food and guns and bullets and hole up in the mountains, because when that happens, the zombies are going to come for you. Well, if you read the paper, that volume they're talking about and these blobs are about 2% partial melt, just like that last picture I showed. That's not, as you said, that's not flowing anywhere. That's not going anywhere. That's not going to erupt. That can't erupt because it's a solid rock with a little bit of melt in the cracks. But if you call it magma, then you get picked up by news sources and so on. And I think this is more than just, you know, an arcane argument, because the community could get in big trouble for this. Imagine if somebody did a study under Mount Shasta and said, yeah, there's a Grand Canyon full of magma under Mount Shasta, and suddenly housing prices in Chico plummeted, and, you know, so forth. The tourism business dried up because everybody was afraid. Then there's going to be a big lawsuit and so on. I think it would be really good if we as a community sort of got our minds around what magma actually is, because it's pretty important. So when I talk about magma, I'm talking about something that is capable of flowing on sort of volcanic timescales. So it has to be less than about 50% crystals, because if it's more than that, then it's more a solid. In order to flow, you have to crack the crystals and deform them. So I'm talking about more than 50% melt. And then here are your tax dollars at work. This is the National Park Service view of Yellowstone. That's Yellowstone Lake there with whatever this is right underneath it. You know, it's like, that's shallow. You can like stop your foot and watch the surface jiggle. So these cartoons, I think, are very pernicious and really lead to bad outcomes. And these are the cartoons we have in our head. These are a couple of intro geology ones. The one on the left is Lyle, 1839, basically. The other one, they all imply there's big bodies of magma under there feeding shallower features. And one that has been published at least a couple of times in the geologic literature is this one, which I find kind of astonishing when you look at it. There's no scale here, but I think if that's a stratovolcano, these squares have to be 1 or 2 kilometers. So that would give you a Pluton that's 5 or 10 kilometers across. If you eroded through it, it would look like the ones on the Chico sheet that I showed you. So this column is 15, 20, 30 kilometers. That's most of the crust. With this gigantic, well, over here, this gigantic column of magma replacing all the rock that used to be there. And if you do a volume, it's like 20, 30, 40,000 cubic kilometers. It's like 20 or 30 super eruptions of magma, replacing all of the rock that used to be there, which conveniently disappears out the bottom of the section, like here, 30 or 40 kilometers down. And this is still molten enough that when another pulse comes in, it pushes that molten stuff out of the way to make room for itself. Now this magma is sitting maybe 500 meters under the surface. You could drill into it for not very much money. The geothermal gradient at the surface would be, I don't know, 1,500, 2,000 degrees per kilometer, and just gigantic gravity anomalies, gigantic heat flow anomalies. You'd have kilometers of surface uplift and all. This is totally unrealistic, and yet it's kind of a natural follow-on from the earlier sort of intro geology ones I showed. There's no evidence for anything like this under any volcano known today. Seismologists have looked really hard to find magma under volcanoes, and what they find is a few percent here. Urubunco volcano in Bolivia, there might be 10 or 15% melt at most, but that's still way too little to flow. There isn't a single place on Earth which is where they found any abundant magma enough to erupt, or enough to a volume of low enough crystallinity that it can erupt. That's kind of a dirty little secret of seismology, but they've looked really hard and they can't find it, which tells us that maybe our picture is wrong. Maybe the big red blob picture is wrong. So I'm going to talk about work that we have done in the exquisitely well-exposed rocks along the crest of the Sierra and down into Yosemite National Park. So Saturday morning, I'm gonna fly home from Fresno, and hopefully it's clear like this. I've got a window seat on the left side, and you can look right up the crest, because you fly right over Mount Whitney, basically, on your way to Dallas. And you can see, here we're looking basically from Mount Whitney up to about Yosemite, up past the Long Valley Caldera, about to Yosemite. And along the crest there, and this is probably not news to many of you, there are a series of nested plutonic complexes that all consist of the same sequence of rocks emplaced in the same order at about the same time. And they all start with intrusion of this dark granodiorite, lots of biotite and hornblende, so it's kind of dark and finer grained. And that's the dark blue unit. Here's Yosemite Valley. So it's on the outside. I'll talk about the Tuolumne intrusive suite in Yosemite and then the Mount Whitney suite, which is very similar. So it's the outermost, oldest unit there. And then those are followed pretty rapidly by what in Yosemite is the half-dome granodiorite. It's this medium blue lobe here. And it's down here in Whitney as well. And then those are followed by this megacrystic unit that has the giant K feldspar crystals that get as big as an iPhone. Okay. And that's in Yosemite, that's the Cathedral Peak unit that's up at Tuolumne Meadow. So that these places spaced about 100, 150 kilometers apart, all were doing the same, making the same stuff at the same time. So we kind of say it's like, you know, many kitchens using the same recipe. We're sort of baking the same stuff up at the same time. Something about the arc, something about the Cretaceous subduction zone that was doing this. We don't know what it was. It's kind of an interesting problem to work on. But there are more of these as you go north into Nevada, and there are at least 2 more as you go south of Mount Whitney, and they're probably the root zones of stratovolcano complexes. There could be something like this baking up under Mount Shasta, Mount Lassen today. And there are volcanic analogs in the Andes that say that that is a reasonable interpretation. So in Yosemite, the blob model has been applied to explain this, and the basic story is that the outermost unit, sorry the colors have changed here, but this outermost unit, which is orange now, came in, and then right after that, the half dome, which is this blue unit, came in and pushed it aside and ate part of it and so forth. And then shortly after that, this middle, whatever color that is, megacrystic unit, the Cathedral Peak, came in and pushed those two aside. And if you take that at face value and say, okay, what is the maximum time that could have taken? Let's bring those magmas in and let's do some thermal modeling where we cool them as slowly as possible. How long might that take? And the answer is less than 1 million years. You have to put those in so rapidly, less than 1 million years, that you get it all in before you have to get the third one in before the first one freezes enough that it doesn't flow and so forth. Now, Yosemite, America's premier national park, back in the 90s, there was no good geochronology done there. Some of the very first potassium argon ages ever done back in the 50s were done in Yosemite. So there are a few 1950s level potassium argon ages, and there were some unpublished cruddy uranium lead ages, and there was another argon age here and there, and there was nothing. And these crummy old ages spanned 10 million years. And Drew Coleman, the geochronologist, and I said, well, you know, we should clean that up. I mean, this has all got to be less than 1 million years. Just go in and do, because he had set up a modern, precise uranium lead zircon lab. He said, let's go see how long this really took. So we went into Yosemite and collected some rocks, and we got answers that we did not expect. And since then, a lot of other people have worked in there because they didn't believe our results, and those are all plotted here, and it's very hard to see what's going on. So I'm going to take all the ages and plot them on this plot where these are the 3 main units. You can kind of skip the one on the right. The 3 main units, the outer, middle, and inner one. And I plotted each point here by its distance from its outer contact to its inner contact. So I'm plotting points from both sides of this symmetrical thing and so forth. And what we found is about a 10 million year span, consistent with the crummy old ages that we were trying to clean up. And more importantly, within the half-dome granite diorite, and the other ones too, but it first showed up in the half-dome, we had ages ranging from 93 down to 89, in 4 million year span. And this could be right, you know. We got a really good age that was 93, and then we got another really good age on the same unit, different sample, same unit, came out saying 90. 3 million years different. And they're good ages, multiple single zircons that gave exactly, well, very precisely the same age. We said that can't be right. So we collected some more samples, collected some from the other side, and reproduced the ages, and we kept getting this pattern of a big range within one unit that should have been one blob, and consistent. The outermost part of the half dome near Yosemite Valley was a lot older than the innermost toward Falling Meadows. So we started to actually believe the data, because we couldn't argue against them. They were really good data. So we said, well, maybe Pluton can have a big range of ages. Because if it's a single blob, it has to cool very quickly. A single blob of that would have cooled within, certainly within 500,000 years. And here we're getting 4 million year ranges. So eventually we let the data speak instead of trying to shut it up and tell it to go away. We said, what if this is true? What if these plutons didn't come in single big blobs? They came in over a long period of time in little pulses. And we pretty quickly realized that a lot of the problems that had bedeviled people about plutons, like how do you make space for all that stuff? You know, when I showed that picture from Glacier Point, everything in the picture was granite diorite. What happened to all the stuff that used to be there? How did you get rid of it? And you have to do that really fast. That's really hard to do. If you do it over several million years, the problem kind of goes away. So we developed this, miraculously got it published in 2004. It's kind of a miracle in retrospect, given how resistant the community was to these ideas. I'm surprised that papers just didn't get rejected, because they're not what we all know must be true. So the next year, we led a GSA field forum. There were 50 people on this field forum. We took them to Yosemite and elsewhere to present the data and to give our field interpretation, our new interpretation of what you see in granites. And we had the cream of the crop of the USGS and Wes Hildreth and Peter Lipman and Charlie Bacon, and all these people were there, and people from all over the world, and they were really hostile. They were having none of this. One person who was very receptive was Allan Boudreau, Hannah's PhD thesis advisor, because he's kind of a radical thinker himself. And he got mercilessly attacked for supporting us. So here we are. This is John Bartley from the University of Utah, and my former student Kent Ratajewski standing at Taft Point with a 3,000-foot drop right behind them. And we'd present stuff, and then pretty much every stop, somebody from the USGS, here it's Tom Sisson, would get up and say, well, that's all very cute. Now let me tell you the way it really is. And he would sort of give the standard interpretation, the USGS interpretation, but it was basically the old interpretation that's in all the books. And it was an extremely tense time for us, but in the past decade or so, I think that the mood has turned, and I think the idea that plutons are composite is accepted by most people because other data sets have come in. The Berkeley Geochronology Center got funded to come in and redo all of our dating to show how we had screwed up, and they got the same numbers and never even published any of it because they just got the same numbers we did. So we're confident in our data and in the data of other people that have reproduced it, and after our data came out and people started to believe it, we had people that would come up and say, I had a data set like that, like in British Columbia on a Pluton, had this big range of ages. I didn't believe it, so I just figured it was bad data. So I give Drew Coleman a lot of credit. Oh no. A lot of...
Yeah, I took care of him.
Don't touch. Do not touch. Like Spinal Tap. So you can look at it. So I think the idea of long lifetimes, the idea that when you look at something like the half-dome granite diorite or any Pluton, that it's composed of lots of little bits of magma that accumulated potentially over millions of years, is kind of getting accepted. And our interpretation of this is that a lot of plutons are basically laccoliths. So here's another commercial plane view. This is Dallas to Reno. If you sit on the right side, you get a beautiful view of the Henry Mountains, which are magmatic blisters punching up through the sandstones of the Colorado Plateau. Really spectacular. G.K. Gilbert, one of the great American geologists of all time, worked out the geology of the Henry Mountains. This is a sketch from his field notebook, which is basically our current concept of a laccolith. This is a figure from his massive report on the Henry Mountains, kind of showing the sediments arched up over the top of it, like a good 19th century geologist. He had a really big beard. He just looked like a field geologist of the male variety. And this is a modern cross-section of the Henry Mountains done by, well, first author is Eric Horstman of East Carolina University, but there's been a lot of work done since then. And this is a lot more complicated than the one that Gilbert drew, but this is the same Mount Hillers, and you see that magma seems to have come up to the Permo-Triassic boundary for some reason and spread out. You had a lot of early sills that are in strata that are now arched up over the top of this blister.